This question is actually from your textbook. So if you look in the textbook, it's exactly the same thing. By the way, has anyone actually done some scuba diving before? Yeah? Do you know what scuba diving is about? Grab on the tank, you go into the deep water, you down, you look at fishies, woo, right? All that kind of stuff. But I don't know if you know this term called decompression, but when you go down, there's this pressure. So when you come back up, you actually can't come back up in one swoop because if you come back up in one swoop, the pressure will, I think, do something to your blood and then you'll pop your lungs and you'll die. Okay, I'm serious. So what happens is people will come up, but they'll come up a certain distance and they'll have to stop for their pressure to kind of get back to normal and then come back up a little bit more. All right. So what happens is, in this case, I'm saying to you the greatest amount of time, which is t in minutes, that a scuba diver can take to rise towards the water surface without stopping for decompression, okay, is given by this function. So t is time, d is the depth, okay? So we're thinking about this scuba diver is going to go down, and he's coming back up, and it says the greatest amount of time he can start coming back up before stopping is given by this formula. Okay. So here's what I'd like you to do. Graph the function using graphing technology. So let's bring out your graphing calculators. Let's see if we can graph this out first of all. Okay. On a test, I know you won't have a graphing calculator. If I give you a question like this on the test, I will actually give you the graph already. Okay. But I just want you to know how to use your graphing calculator as well. So let's take a look at this. So I'm going to ask you to graph this out. So go to y equals 2 and let's plug in the function 525 divided by, and then we don't have d, so we'll use x. Make sure you put a bracket, okay? So this is one mistake a lot of people do. That d minus 10 is the entire denominator, so please put a bracket around the x minus 10, okay? Then you might want to press graph, and you press graph, you're like, where's my graph? So think about this, okay? Think about your domain and all that kind of stuff. My window right now is really, really small. What do you think my window should be? The standard one? Okay, I'll try standard first, but I heard someone say 500, so I think that's interesting. Here's standard. Still no good. 500, someone said? Oh, zoom out once? Okay, let's zoom out. Maybe I'll do that. Zoom out once. Oh, I see something now. Ooh, that's good. Oh. What do you think this thing is, dear friends? The vertical asymptote. What value of x is this vertical, or d, I guess, is this vertical asymptote? Look at your equation. How do I find the vertical asymptote from the equation? Yeah, good. The denominator equals to 0, right? So therefore, d can't be equal to 10. There's your vertical asymptote. Okay. If this graph's not good enough, let's zoom out one more time, perhaps. So I'll zoom out one more time. And maybe this is a pretty, maybe that's no good. But whatever. Okay. I will say to you, let's do some quick sketch like this. Okay. So here we go. And then I believe at 10 you have this vertical asymptote. And if you kind of did a quick sketch, the graph looks like this. Whee! And then whee! Okay. Now, I don't know which window coordinates you'd like to use. Maybe I'll go back to Dayon's graph before, zooming out twice. Maybe I'll just use this graph. Dayon, is this one that you like? You like this one here? Sure. So your window coordinate is negative 40, 40. So I will say here, let's say this is negative 40, 40. This is negative 40, 40. And then let me just label this. The x-axis is your depth, and your y-axis is your time. So this is a little bit different than what you do in physics, because a lot of times when you do physics, time is always your independent on the horizontal axis, because this one's a little bit different. Isn't the bottom one negative? Yeah, negative. Yeah. Ha ha ha. Just joking. Thank you. Okay. Now, my next question to you is a little bit more fun. It says, determine a suitable domain which represents this application. So what's a suitable domain for this situation? Domain, of course, we're talking about the horizontal. We're talking about depth. So what do you think are valid answers for depth? What are some possible values for depth? 10? Not 10. Okay, anything not 10. So Alex, you're saying, hey, the depth can't be 10, but it can be everything else. Agreed? Oh, you don't know. Okay, but what do you guys think? Greater than, Caleb says? Greater than what? Greater than 10. So What's wrong with all this stuff over here, Caleb? Yeah. How can time be negative? Let's go back in time. No, it doesn't make sense. So technically in this situation, okay, because in this situation we've got context, this is not the correct domain. It would be if it was just a graph, but because in this situation, I'll say in this situation, the correct domain would be d is greater than 10. Because those are the only parts of the graph which give you a time that is positive. Okay? So in this situation, d has to be greater than 10. And I'll say because we need time to be positive. Good. Okay? So once again, I want to reiterate. The expression in green here, d does not equal to 10, d is all real numbers. That is correct if we just look at the graph. But because we've got context to it, we need to say, hey, this domain is a little bit different. It's only when d is greater than 10. That makes sense. Okay? All right. Let's do the next one then. How would you do this? Determine the maximum time without stopping for a scuba diver who is 40 meters deep. How do we do that? Yeah, plug in d equals to 40. So you can just plug it into the formula if you wish. So t equals to 525, and then it's 40 minus 10. That's perfectly fine. But for those of you who have your graphing calculator handy, what could you do instead? Use your graph, right? How about using some of these functions? Second trace. Do you remember which function I use here to figure out the y value? Value, yeah, and then type in x equals to 40, and then press enter, and oh, look at that. There's my point. 17.5. Okay? 17.5. Seconds? Minutes. Yeah. Seconds, that's pretty bad. If you can only dive for 10 seconds and come back up and stop. Right. Okay. Now, how about the next part here where it says graph a second function t equals to 40. Then I want you to find the intersection points, and then I want you to interpret this point in terms of this situation. So what I'd like you to do now with your graphing calculator is let's see if you can figure out what the value is first. So I need t equals to 40. Perhaps you plug in y2 as 40. And then what are we looking for? The intersection point. Now, I guess this graph's not so great right now because I probably want to see more of this. I'm going to quickly change my window to make it look nicer. Do I need x min to be negative 40? That's really far, right? Let's just go to 0. Maybe I'll make x max a little bit bigger, 50. But my y min and y max I better change. How about my y min being 0? How about my y max being 100? And this, I think, gives us a better graph. Okay. And then what are we looking for here? The intersection points. For those of you who have your calculator, go ahead and do this, please. Second calc. Choose number 5. And then I'll say, yeah, that's my first curve. Press enter. That's my second curve. Press enter. Press enter one more time for a guess. Hey, there we go. 23.125. Okay, so let me just ask you to quickly do this now. I'll just do a quick sketch. Here's our graph. And then here's the line t equals to 40. And we're looking for the intersection point, which we found to be 23.125, 40. Now, we found the intersection point. There is only one of them. Okay, by the way, you might be thinking, Mr. Lee, there's another one over here, that straight line. Remember, that's a vertical asymptote. It's not really there. Okay, so don't think of this as an intersection point. No way. Okay. So, you've got this number. Can you interpret what this number actually means? So t equals to 40. I'm saying the time is 40 minutes. What's the other number represent? The depth. Right. So what does this represent here? It's the depth, how deep he is. Or it tells you that the diver has 40 minutes, a maximum of 40 minutes to do his diving if he goes to a depth of 23.125, in this case, meters. So let me just write down something like this, and I'll use the answer in the book too. It says the diver, okay, so the diver has a maximum time of 40 minutes Okay. Before, I guess, what does it say? Before stopping for decompression. Stopping for decompression, so you don't kill yourself. If he is at a depth of, and I'll say 23.125 meters. Okay. Okay. Now, that's the answer. And of course, if you didn't have your graphing calculator, you're thinking, on the test, Mr. Lee, how would I do this? Well, remember, here's your formula. T equals to 525 d minus 10. If you want to solve for d, just plug in t as 40. Yeah. And then I hope you know how to solve this. Cross multiply. Will that help you out? Right, and solve? So I won't do that for you, but you can figure that out. Okay? Oh, I'm sorry, I'll move back over. Yeah. Okay. Now, the last one, since someone asked me, do we have to know horizontal asymptote stuff? And yes, you do. Let's give you one more chance to practice this together. So does this graph has a horizontal asymptote? Well, you can take a look. Does it look like it has a horizontal asymptote? No? What if I went back to like zoom? Oh, zoom standard doesn't work, right? Zoom out. Okay. Do you think it has a horizontal asymptote? Seems like the graph gets like further and further, getting closer and closer over here too. Let me zoom out one more time, maybe. Zoom out one more time. Can you see if there's a horizontal asymptote in this? Oops, I zoomed the wrong way. Sorry.
Wait, but wasn't there like a line on top?
That line on top was the asymptote, right? Oh, not that. Sorry, that was the line y equals 0. There we go. That's better. Here's our graph. This is the asymptote. This is that line 40, so don't worry about that. Okay, but do you see there's an asymptote for a horizontal one? Let me zoom out one more time. Can you see it now? There's a horizontal asymptote? Looks like the asymptote would probably be somewhere right here. Agreed? So now the question is, what's the equation of that line? How do we find that out? So let's calculate this algebraically. Remember, the key thing is to take the limit, and please write this down, as x approach to infinity of the function 525 over, now, oops, I made a mistake. There's no x in this function, is there? It's d, right? Oops. So what should I use instead of x? D, yeah. Okay, and I made that mistake on purpose, so you'll know too. For those of you taking AP Calculus next year, if you write down x and there's no x in the actual function, they'll be like, what are you talking about? They'll mark it wrong. Okay. So, how do we figure this out? Do you remember we always want to factor out the highest power of the variable? In this case, there's no variable on the top, so we'll leave it as 525. There is a variable on the bottom, which is d, so we'll factor that out. And then I'm asking you to take the d minus 10 and divide it by d. So d divided by d is 1. What's negative 10 divided by d? Negative 10 over d. Okay. You're thinking, ew, this looks nasty. You're right, it does. But there is a fact that we say when the limit as x approaches to infinity of 1 over x to the power of n, what is this always equal to? 0, yeah. Take 1 divided by a big number, it's always 0. Take 1 divided by a big number all squared, still 0. Take, yeah, you get the idea. Okay. So that's 0. What does this thing become? 0, right? So what we have left over here, and I should put a limit in front. Why does it become 0? So because if I plug in a big number to just this part, 10 divided by a really big number is almost like 0. Okay? So what we have left over is the limit of d approach to infinity of 525 over d times 1. Well, that's just the same thing as the limit as d approach to infinity of 525 divided by d. And can someone tell me what this is equal to, probably? 0. Yeah. 525, yeah, that's a big number, but dividing by infinity, an even bigger number, hey, look at that, it's 0. So therefore, I'll just say the horizontal asymptote, okay, is that the d value equals to 0.
Is that for every every single horizontal asymptote?
Okay, now ladies and gentlemen, good question, Rebecca. Rebecca say, hey, Mr. Lee, is it true that for all horizontal asymptotes the equation is d equals 0? Well, for reciprocal functions, the answer is yeah. Why? Why is it always equal to 0 for reciprocal functions? What's the definition of a reciprocal function? On the top is always usually a 1 or some other number, right? Where are your variables for a reciprocal function? On the bottom, right? So you plug in a big number, 1 divided by a big number is always going to be small number, like 0. So for reciprocal functions, yes, the horizontal asymptote you can say is always going to be 0. However, if we go back to chapter 6, when we do stuff like this, where I had rational functions, okay, like this, I don't know, 5x minus 4 or 5, these ones are not necessarily always equal to 0, because in this case, you can simplify and you might get like a number, okay, and you might get like infinity, or you also might get something like 0, okay? So for rational functions, this is the extra stuff I taught you from chapter 6. Not always true, but for a reciprocal function, you bet it's always 0. Okay? All right. I think I'll stop here for today. Let me just tell you that you should be trying to finish off all the homework from here. Okay? And if you haven't, well, guess what you're doing tonight and tomorrow? Okay?